Hello, welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. Alright. So, currently we are looking at the MMSE estimate of the parameter h and from an observation y when the parameter h and the observation y are jointly Gaussian, and towards this end we have derived the joint density of this h parameter h and the observation y, and that is given by this quantity, that is shown here. That was done in the previous module, that is the joint probability density function of the parameter y of the parameter h and the observation y when the parameter h and the observation y are jointly Gaussian. All right. So, now as said before, we need the conditional probability density function. I need the conditional probability density function of the parameter h given the observation y, which is basically, as we already said, this is the joint probability density function of the parameter h, observation y, divided by the marginal probability density function of the observation y, and this now I am going to simplify by writing the exact expression for each. Okay. So, the first is the joint probability density function, that we have already derived the expression. So, that is square root of 2 pi whole square, 1 minus rho square, that is your determinant r, which is sigma h square sigma y square e to the power of minus half 1 minus rho square sigma h square sigma y square h square sigma y square plus y square sigma h square minus 2 rho sigma h sigma y into h y divided by the marginal probability density function of y, the observation y. We said the marginal probability density function of the observation y is a Gaussian random variable with mean 0, variance sigma y square. Therefore, this we have already derived, this marginal probability density function of this observation y, this is given as 2 pi sigma y square e to the power of minus half y square divided by sigma y square, and therefore, now I can simplify this. First, let us simplify this quantity, that is the multiplying factor. This is under root 2 pi 1 minus rho square sigma h square sigma y square divided by sigma y square. So, this gives 1 minus simply 1 minus rho square times, this gives 1 minus rho square times sigma 1 minus rho square times sigma h square into multiplied by, this is a large term, minus half of first, which is basically your 1 minus rho square sigma h square sigma y square h square sigma y square plus y square sigma h square minus 2 rho sigma h sigma y h y, correct, minus this quantity minus y square divided by sigma y square. All right. So, this is the quantity in the exponent. Okay. This is multiplied by, this is the multiplication signal, and this is the quantity in the exponent. So, this is the quantity in the exponent, all right, e to the power of minus half times this quantity. Now, let us simplify this quantity in the exponent. So, I want to first start by simplifying this quantity in the exponent, and then we can simplify the rest of the expression later. Okay. And this quantity in the exponent, that can be simplified as follows. Let me just write it down. It is a bit cumbersome, but this is fundamentally important in MMSE estimation. So, it is worth going through this derivation at least once, that is h square sigma y square plus y square sigma h square minus 2 rho sigma h sigma y h y divided by 1 minus rho square sigma h square sigma y square minus y square divided by sigma y square, and this is then I can combine these two, 1 minus rho square sigma h square sigma y square h square sigma y square plus y square sigma h square minus 2 rho sigma h sigma y minus y square into 1 minus rho square sigma h square, that is the term I will get over here. Now, observe this quantity, I have y square sigma h square, and if I expand this I will have a minus y square sigma h square, right. I will have a minus y square sigma h square coming from these two. So, those two terms, so this term will cancel with this part, and what I am going to be left with, interestingly, if you observe this, is h square sigma y square, something very simple, this y square sigma h square cancels. What I am left with is y square rho square sigma h square. So, I am left with y square rho square sigma h square minus 2 rho sigma h sigma y h y 1 minus rho square sigma h square sigma y square. And now, if you look at this quantity in the numerator, that is nothing but, observe that this quantity is nothing but h sigma y minus rho sigma h y whole square, because look at this is h square sigma y square plus rho square sigma h square y square minus 2 rho sigma h sigma y h into y. Okay. So, this is nothing but h sigma y minus rho sigma h y whole square, and once we have that, the rest is very simple. This is 1 minus rho square sigma h square sigma y square, and now take sigma y out common from the denominator and numerator, that is sigma y square common from the numerator and denominator. What I am going to have is h minus rho sigma h by sigma y into y whole square divided by 1 minus rho square, because sigma y square cancels from the numerator and denominator, 1 minus rho square sigma h square. So, this is basically your quantity in the exponent. Quantity in the exponent will be e to the power of minus half times this. This is the your quantity in the exponent. Therefore, now the conditional putting it all together, remember we set out to derive the conditional probability density function of the parameter h given the observation y. Therefore, now the conditional probability density function of the parameter h given the observation y, conditional probability density function, this will be given as follows. This will be given as, this is the multiplying factor is 1 over square root 2 pi 1 minus rho square times sigma x square e to the power of minus half. Now, you can look at this e to the power of minus half h e to the power of minus half h minus rho sigma h by sigma y whole square divided by 1 minus rho square sigma h square. Okay. So, this is the joint probability density function. Now, what I am going to do is basically I am going to set this quantity as sigma tilde, that is I am going to define two new quantities, sigma tilde equals or sigma tilde square equals 1 minus rho square sigma h square and mu tilde equals this quantity over here I am going to set as mu tilde equals rho sigma h by sigma y times y. And now, you can see something very interesting. Now, if I write this joint, if I write this conditional probability density function, what I am going to observe is that f of h given y of h given y equals 1 over what you are going to observe is something very simple, 1 over square root 2 pi sigma tilde square e raised to minus half, e raised to e is nothing but the exponent, e raised to minus half h minus mu tilde whole square and look at this, this is again your sigma tilde square divided by sigma tilde square. And now, if you look at this, you will realize that this is a Gaussian distribution with mean mu tilde and variance sigma tilde square, and that is the interesting aspect of this. So, this is basically again, now when you see this, this is, you can see that this is basically a Gaussian distribution with mean equals mu tilde variance equals sigma tilde. Therefore, what you can say is that the posterior, remember this is also known as the posterior probability, the conditional probability density function of the parameter h given the observation y, this is also the a posteriori probability density function. This is Gaussian, right. So, h given y is basically Gaussian distributed with mean mu tilde variance sigma tilde square, and therefore, now you can clearly see expected value of h given, and this is very straightforward. Now, you can see the expected value of h given y equals mu tilde, which is nothing but, now you can see what is mu tilde. Mu tilde is basically this quantity over here, that is your rho sigma h by sigma y times y. So, this is your rho sigma h over sigma y times y, and indeed now we have found the MMSE estimate, because what is the MMSE estimate? MMSE estimate, the minimum mean squared error estimate, remember the optimal minimum mean squared error estimate, that is the estimate which minimizes the mean squared error, is nothing but the expected value of the parameter h given the observation y. Therefore, this quantity mu tilde is nothing but the MMSE estimate of h given y for the scenario when h and y are jointly Gaussian. Okay, that is something to keep in mind. So, this is basically your MMSE estimate. So, let us also write that down clearly. It requires some manipulation, but the end result is very simple and clear. So, this says that MMSE estimate H hat equals expected value of H given Y equals rho sigma H divided by sigma Y times Y. This is the MMSE estimate of. So, this is the MMSE estimate H given Y for H comma Y, that is the parameter and the observation, when the parameter and observation are basically jointly Gaussian random variables, all right. And now, what is this quantity? Sigma tilde square, this quantity, this is your mean squared error. This is the mean squared error, right. So, this is the mean squared error. What is this? This is the expected value of the parameter H minus H hat whole square given of course the observation Y. And what is this quantity? This quantity you can see is 1 minus rho square times sigma H square. So, this is the mean squared error. This is the mean squared error. This is the mean squared error, and something very interesting can be observed from this mean squared error. What is the interesting thing that you can observe from this mean squared error? Consider two particular cases. If, so let us write this as interesting observation. Consider the simple case, if rho equals 1, remember the correlation coefficient rho we said can lie between -1 or 1. Okay. Now, correlation coefficient of 1 basically means Y and H, that is the observation Y and the parameter H are statistically identical because the correlation is perfect, that is the correlation is the maximum value of 1. On the other hand, if rho is -1, they are also statistically identical in a different way, that is H is basically minus Y and Y is minus H. Okay. So, basically in both these cases we see, that is when the correlation coefficient rho is equal to 1 or the correlation coefficient rho is -1, rho square is equal to 1. Therefore, 1 minus rho square is 0, which means the MSE is 0, and that is naturally true because if the correlation coefficient is 1, on observing Y you know that H is identically equal to Y, and when correlation coefficient is -1 on observing Y you know that H is equal to -Y. So, there is no error, in that sense the mean squared error is 0. When there is perfect correlation between the observation Y and the parameter H, the mean squared error is 0, and that is an interesting implication from this derivation. So, if rho equal to 1 or for that matter -1, we have this implies 1 minus rho square equal to 0. So, in this case what we can see is, in this case H is basically equal to Y or H is basically equal to -Y. H can be perfectly estimated. So, a colloquial way of saying is H can be perfectly estimated on Y since the correlation is -1 or 1. Okay, if the correlation is 1, H is equal to Y. If the correlation is -1, H is equal to -1. Now, consider the other scenario. If rho is equal to 0, that is implies the correlation between H and Y is 0, implies 1 minus rho square equals 1 implies MSE equals, what is the MSE? You can see 1 minus rho square is equal to 1, MSE rho is equal to 0, MSE is simply sigma h square, the mean squared error is simply sigma, that is initial variance which is equal to initial variance of the parameter h, which means having a, because the correlation between the observation y and h is 0, right, the observation y does not convey any information about h. So, observation y cannot be used in any meaningful sense to get an estimate of the unknown parameter h. Therefore, the variance of h, that is the parameter h, is sigma h square to begin with. Even after making the observation y, the variance of h remains at sigma h square. Therefore, having observed y does not make any impact or does not convey any information about the unknown parameter h. So, these are two extreme cases which yield interesting insights into the behavior of this MMSE estimate. And now you can see for different values of rho between 0 and 1, the variance can go all the way from sigma h square, that is when rho is equal to 0, the variance is sigma h square, when rho is equal to 1, the variance is 0, and between when rho increases, as rho increases from 0 to 1, the variance decreases or the MSE decreases from sigma h square to 0. So, that is an interesting observation that one can make from this MSE, the mean squared error per se of this MMSE estimate that we have derived for the jointly Gaussian scenario. All right. So, now let us also simplify this MMSE estimate and the variance to give alternative expressions which are more convenient. All right. So, we have already said, what have we already said? We have already said, if you go back to our nomenclature and if you look at our definitions, from our definitions what we have is basically we have that expected h square equals sigma h square, let us denote this by r h h, expected y square equals sigma y square, let us denote this by r y y, just denoting this by the variance by r h h and the variance of y by r y y, and the cross correlation between h and y, this we can denote by expected h comma y, we denote by r h comma y. So, let me just repeat those definitions over here, so that it becomes convenient. Let us define your sigma h square as expected value of the parameter sigma h square equals expected h square equals sigma h square equals r h h. Let us define expected value of y square equals sigma y square as r y y, and let us define the expected value of h y which is equal to rho sigma h sigma y as r h y. Now, if you look at the MMSE estimate, the MMSE estimate is h hat, which is the expected value of h given y, which is also, you can see from this, rho sigma h divided by sigma y times y. So, this is basically your rho sigma h divided by sigma y times y, and now I can simplify this as follows, that is rho sigma h sigma y multiplying and dividing by sigma y, I have rho sigma h sigma y divided by sigma y square times y, which is now, if you look at this quantity here, this is basically your r h y, and this quantity in the denominator is basically your r y y. So, I can write this as something that is going to be helpful in our later discussion, r h y times 1 over r y y, which is basically r y y inverse times y, and this is a very interesting expression, because the same expression can be carried over also for the matrix scenario, that is when h and y are vectors. All right. So, I can write the estimate h hat as r h y times r y y inverse times y. Now, of course, when h and y are vectors, the interesting thing is I can replace r by y by the covariance matrix of y, r h y by the cross covariance matrix between the parameter vector h and the observation. So, this is a very interesting way to write this, because this is a very convenient expression to remember, and that can also be used in various other much more complicated scenarios, such as a vector scenario when y is a vector, when h is also a parameter vector, alright. Although the expression that we have derived, which is rho sigma h divided by sigma y times y, is equally valid, this is much more convenient and a much more standard form to remember this expression. And the expression for the MSE can be simplified as, so this is the expression for the MMSE estimate, and the expression for the MSE, this can be simplified as follows. This is equal to 1 minus rho square sigma h square, which is basically your sigma h square minus rho square sigma h square. Now, of course, this quantity here we already know what this quantity is. This quantity is r y y. So, this is I am sorry, this quantity here is basically your r h h. So, this is basically r h h minus, now this quantity I can write as rho sigma h times rho sigma h. Now, this quantity I will again manipulate as by multiplying and dividing by sigma y square, rho sigma h sigma y into 1 over sigma y square into rho sigma h sigma y. Now, you can see this quantity is r h y, this quantity here is r y y, and this quantity here I can write it as r y h, because for the scalar scenario r h y equals r y h, which might not be the same as vector scenario. In fact, r h y is r y h transpose for real vectors. So, this is r h y into r y y inverse into r y h, and this is your convenient expression for the MMSE. In fact, this is not just the MMSE, but this is the MMSE. This is in this case, this is the minimum mean squared error. This is not just the MMSE, but for this particular scenario, this is the MMSE, that is your actual minimum mean squared error. So, we have found two things. One, we have found the MMSE estimate, that is rho sigma h sigma y divided by sigma y square into y, which is basically r h y times r y y inverse into y. And also we have found the actual value of this minimum mean squared error, that is MMSE, which is r h h, that is sigma h square minus r h y into r y y inverse into r y h. This is your mean squared error for this scenario. Okay. So, that basically completes this derivation, where we have started with jointly Gaussian random variables h and y, where h is the random parameter, y is the random observation. We have considered them to be jointly Gaussian in nature, alright. And following this, we basically derive the conditional probability density function of h given y, using the joint probability density function of h and y and the marginal probability density function of y, and basically from that we inferred the conditional probability, the conditional mean of the unknown parameter h given the observation y, which is in fact the MMSE estimate, alright. And we also found the mean squared error, or rather in this case also the minimum mean squared error. Okay. So, we will stop this module here and we will continue with other aspects in subsequent modules. Thank you very much.